As the text states, modules 18, 19, and 20 deal and address the broad topic of our senses and how we sense and perceive the world. Module 18 considers some basic principles that apply to all of our senses. Module 19 takes a look at sensory perceptual processes and vision. And Module 20 reviews our non-visual senses. We have chosen to focus on Module 19, which deals with vision. The module is subdivided into two main sections, sensory input and perceptual processing. For our project, we would like to focus on the second subsection, perceptual processing, or how our brain converts sensory input into meaningful perception. The first half of Module 19 covered how we process incoming sensation from the outside world. As the diagram on the screen shows, this is how we take the incoming sensory sensations and transform them into neural impulses that are sent to the brain. The brain does its magic, and as a result, we can see. But this is only half of the vision story. The second half is how does the brain organize and interpret these incoming sensations and turn them into meaningful perceptions of the world. The purpose of this presentation is to examine just how the brain does this, takes in visual sensations, processes the information, and comes up with reasonable perceptions, or at least most of the time. Our goal is to leave you with the impression that seeing is truly believing, but also that seeing may be truly deceiving. In the early 1900s, a group of German psychologists observed that when people were given a cluster of visual sensations or sensory stimulations, they tended to organize them into what they referred to as a gestalt. And Gestalt is a German word that means form or the whole. And these Gestalt psychologists, as they became referred to, went on to demonstrate many of the principles our brain uses to organize our sensations in meaningful perceptions. Underpinning all of their principles was the idea that our brain doesn't simply take in information about the world. Perception is not just opening a camera shutter and letting a picture print itself on the brain. We filter incoming information and from that information construct perceptions. So in essence, mind does matter. One of the first perceptual tasks that the Gestalt psychologist emphasized was our ability to perceive any object, let's say a person's face, and what they would refer to as the figure, as being distinct and different from the background information, which they called the ground. This led to the concept referred to as figure ground. And this is an example on your screen of the figure ground relationship. Notice the 3 hourglasses in the figure, and they are the central organizing stimulus. They are the ground. But did you also know the surrounding information, the figure, which is the arrows? So this is an example of figure ground. The hourglasses, the 3 hourglasses are the figure or the central focus of the image. But the surrounding background, the ground, is the 4 arrows. Here is a familiar image I'm sure all of you have seen before, and it's a classic example of figure and ground relationship. As you can see, there's a large black image of a vase, which is, in this case, the central image or the figure. Also, if you examine the white space, you'll notice the profile of 2 faces. In this case, the background information or the ground. On the surface, this appears to be a reasonable interpretation of the incoming sensory data, but there's something a bit confusing about the image. For me, my mind keeps jumping between seeing the vase as the central image and then seeing the 2 faces as the central image. And if I remove the box that frames the image, it even becomes a little more confusing. What is it we are actually seeing? Is it a vase? Is it two profiles of people? Is it both? The confusion stems from what is referred to as an ambiguous image or a reversible image. Let's look at a few more. This is a classic duck-rabbit ambiguous image we all have seen before. What's interesting about this image is not only is it ambiguous, is it a duck or is it a rabbit, but it represents a class of images that are referred to as multi-stable perceptions. Now, multi-stable perceptions are images that provide multiple, although stable, realistic perceptions. When your brain encounters these types of images, it is confronted with a problem. How does it interpret this sensory information? Since both the duck and the rabbit are reasonable choices and both have about a 50% chance of being correct, your brain goes back and forth between them. But the question remains, what is the actual reality? Or maybe more appropriately, is there an actual reality? Here is another example of a multi-stable perceptual image. Take a look at it. How does your brain initially interpret this image? Is there a single reality here? Do you see a face of a woman? Or do you see a face or a caricature of a gentleman playing a saxophone on the left side? What is the reality here? It is difficult to distinguish in this particular image between what is figure and what is ground. Let's take a look at another one. Well, this is a classic one, my wife or my mother-in-law, another common multi-stable perceptual image. What do you see here? Again, the question is, what is the reality, if in fact there is a reality? Again, the question is, what is the reality? Or, as I said before, in fact, is there really one? Do you see an old woman, or do you see a young woman? Ambiguous and multi-stage perceptual images present the brain with a challenging task when it comes to interpreting the sensory input. But now let's take a look at some other sensory challenges that the brain faces. One very interesting feature of our brains is that it does not tolerate ambiguity or incomplete data. If it receives incomplete or ambiguous sensory information, it will either fill in the missing data or resolve the ambiguity. In some ambiguous images, an illusion is often produced from what are referred to as illusionary contours or lines. An illusionary contour or line is a perceived contour or line without there actually being a contour or a line. Let's take a look at this example. What you see are three hands that are apparently holding a white triangle. The problem is, there is no white triangle. Your brain has fallen victim to the illusionary contour effect. Since the incoming sensory data is incomplete, your brain manufactures a solution by producing the illusion of the triangle where none actually exists. Again, another example of the illusionary contour or line effect and your brain's attempt to make some sensory sense out of the ambiguous data it has received. Even knowing the truth that there is no triangles present, your brain still doesn't change our perception. Let's take a look at some other ways the brain deals with incomplete or ambiguous sensory data. Take a few seconds and read this sentence to yourself. Did you understand the meaning of the sentence? There are 34 words in the sentence. Only 10 words are spelled correctly. That means 24 words, or 71% of the words, are spelled incorrectly. Yet you were able to read and understand the meaning. This is another example of the brain compensating for incomplete sensory data and filling in the ambiguous information. Take a look at the visual sensory stimulus on your screen. What do you perceive? It says, think the eyes have it. Again, another example of the brain's attempt to make sense out of ambiguous data. So far, we've looked at several ways that the brain attempts to make sense out of the incoming sensory data. We've seen 2 examples of how the brain attempts to recognize the figure and ground in sensory input. We've seen 3 examples of how the brain deals with ambiguous or multi-stable incoming information. And finally, we've looked at 4 examples of how the brain compensates for incomplete or ambiguous data by filling in the gaps the best way it knows how. What is amazing is that, as incredible as the brain is in taking in and perceiving incoming sensory data, many times it is incorrect in its interpretation. We're going to now take a look at how color and shading may affect how the brain interprets data. Color and shading can have some very strange effects on the brain and how it correctly perceives incoming sensory input. Take a look at the areas of the sofa labeled A, B, and C. Now, in terms of what your brain is showing you, what 2 areas, A, B, or C, are the same color or shade? As amazing as it may seem, areas A and C are exactly the same shade. Let's look at one more example before we explain the underlying principle. Here we have 2 similar rectangles, each inside a larger rectangle. According to the information your brain is supplying you, which of the 2 smaller rectangles is the darker shade? Again, amazingly, they both are the same shade of gray. Here is the effect of shading or color on the brain. An object surrounded by a darker object will appear lighter in color or shade, and conversely, an object surrounded by a lighter shade or color will appear darker. Here's a final example of how visual stimulus like shading or color can be distorted by surroundings. Going back to our figure and ground interpretation of visual information, on your screen are 2 blue stars, they are the figures, surrounded by black and white bars, which we'll call the ground. Your brain is telling you the top blue star is darker in color than the bottom blue star. But the reality is both stars are exactly the same shade of blue. But it is the context in which they are placed in that tricks the brain into seeing differently. Perspective, or the conditions surrounding the sensory incoming data, has a great deal to do with how our brain interprets the incoming information, the perspective that the data is presented in. So here we have a painting by an Italian artist. And the saying is on the top, when you change the way you look at something, you change the thing you look at. Now I've rotated that painting 180 degrees. And now we have somewhat of a caricature of a face. Now we have the painting. Now we have the face. Again, the perspective that information comes in determines how the brain may interpret that information. Another example of how perspective, or the conditions surrounding the sensory incoming data, has a great deal to do with how the brain interprets the incoming information. Take a look at this image on your screen. And by rotating it, you're seeing different images, although it's exactly the same image. Here is another beautiful example of perspective and its effects on the brain and how the brain interprets incoming data. We have three ancient soldiers walking down a road. Now, relying on what your brain is telling you, which soldier is the tallest, or are they all the same size? Let's take a look. Now that soldier right there in the front closest to us seems to be the smaller. But actually when we move the line up, the soldier that appears to be smaller is actually 15% taller than the soldier that appears the tallest. The interesting perspective principle at work here is that objects that appear further away from us appear to be larger, and objects that appear nearer to us appear to be smaller. Again, the brain has a totally distorted view of reality here. Again, here's another example of how perspective affects how the brain interprets incoming data. What is your brain telling you about the relationship between line AB and line CD on the image on your screen? Which one appears larger? Well, let's take a look. They're both basic, they are exactly the same size. Once again, the brain has difficulty correctly interpreting incoming sensory information and creating a meaningful and valid interpretation of reality. Okay, this is our final example. What does your brain tell you you are seeing? If you are over the age of 6 or 7, you most likely see a naked man and woman in a romantic embrace. However, if you are under the age of 6 or 7, you most likely see 7 or so dolphins. The reason for this effect is that young children do not have the schema for romantic or sexual love, and therefore they don't see that, whereas you and I do have that schema built in. So we don't see the dolphins initially. We see the man and woman in a naked embrace. Again, the brain has a difficult time interpreting incoming sensory information sometimes. Well, that's it. For all the complex and fascinating things neuroscientists have discovered about the human brain, it still remains the most mysterious part of our bodies. One thing we do know is that the brain's interpretation of the world is not always literal or correct. When it comes to perception, our brain is good at filling in gaps and drawing visual conclusions that may or may not align with reality. In an effort to keep our surroundings familiar and understandable, our brain takes a few liberties here and there, and for the most part, we usually are unaware. The purpose of this presentation was to point out some of those liberties that the brain does take, and to shine some light on the underlying causes of these liberties. Thank you very much for your time and consideration.